It's a real pleasure, my lords, ladies and gentlemen, to welcome you here this evening to our New Year reception. We are now beginning our 40th anniversary year, and I'd like to take this opportunity to thank you all for your enthusiastic and ongoing support that you provide for the Academy's activities. And I'd also like to take this opportunity to express my gratitude for the encouragement and help that many of you have given me personally during my first year as president. And in particular, I really do want to thank Philip and the staff of the Academy for the phenomenal job that they do. Our senior fellow, His Royal Highness Prince Philip, chaired the first meeting of the Academy, or the Fellowship of Engineering as it was then known, at Buckingham Palace in June 1976. And I hope you had the opportunity to hear Prince Philip's interview on the Today programme on the 2nd of January, when Lord Brown, one of our past presidents, was guest editor. If you haven't heard it, it's still available on iPlayer, and I really commend it to you, because when you listen, you will hear the quote of the year from Prince Philip. Everything that wasn't invented by God was invented by an engineer. It's a quote we're going to use time and time again, not just this year, but forever. 2015 was another tremendous year for the Academy. In November, Her Majesty the Queen presented the Queen Elizabeth Prize for Engineering to Dr. Robert Langer of MIT. He was the first person to engineer polymers to control the delivery of large molecular weight drugs to treat diseases such as cancer and mental illness. News of that prize reached over 1.5 billion people worldwide. Another prize this year was the inaugural Africa Prize, which was presented in June to Dr. Oscar Hilonga. He's a chemical engineer from Tanzania who's developed a sand-based nanofilter that could dramatically improve the safety of drinking water at low cost. After winning our Africa Prize, he went on to win the prize at the Duke of York's Pitch at the Palace event for Africa. He made his pitch in front of 7 African heads of state, as well as business leaders and venture capitalists, many of whom offered immediate support towards the development of nanofilter. And you might be reassured to know that Academy Fellows are providing mentoring and advice to help Dr. Hilonga make the most of those opportunities. We spent much of the last year advising government on research and innovation policy in the lead up to the spending review. At the request of the Science Minister, I conducted a review of academia business research collaboration, and the Academy also published 2 reports emphasizing the economic benefit of public funding for innovation and for engineering research. We also held a month-long exhibition on engineering for growth in the foyer of the Department of Business, Innovation and Skills. In the event, we were pleased that research came out very well in the spending review, with constant funding in real terms for the next 5 years. Funding for innovation was better than feared, with level funding in cash terms. However, this does not mean no change. The government is consulting on wide-reaching changes to the forms of innovation and industrial support, and to the funding of further and higher education. We're working with partners across engineering and with the other academies where appropriate in responding. Moving on to this evening, our events programme is a core part of the Academy's activities, And we're very grateful to our forum partners for their generous support. I hope you'll join with us in as many events as possible in 2016, and these include a special anniversary awards dinner on the 23rd of June in the Pavilion at the Tower of London. Before I introduce our speaker, we're going to present the inaugural Royal Academy of Engineering Armourers and Braziers Company Prize for Excellence in Materials Science. This £2,000 prize celebrates success in applying novel materials science and technology to practical engineering systems. To tell us more about the prize, please welcome Professor Bill Bonfield, Chairman of the company's Materials Science Committee.
Thank you, President, ladies and gentlemen. It's a great pleasure to be here on what for us is a very special evening. We started before you, we actually started in 1322. And the guild then was the Guild of the Armourers, and at that time around Coleman Street, where we're still based, there are about 50 small furnaces, of course, making armours, so early examples of engineering activity. Much later, 1708, you might think that's when we merged with Scotland, but also that's when the armourers merged with the braziers, because by then armour was no longer in fashion, but brass and copper, particularly for the tourists, was in fashion. And so the braziers who worked in copper joined with the armourers. So the armourers and braziers, I think, was actually the first example of ferrous and non-ferrous metallurgy coming together. Nowadays, of course, we're not involved in productive activity, but the benefit of that heritage is that our assets are used to help fund education. And the Gauntlet Trust that we established some 40 years ago, similar to the Academy here, is involved in giving money each year to worthy causes in education and science, and particularly to encourage the pursuit of material science. And we do this through a whole range of activities. In fact, we have partnerships with industry, with Tata, Rolls-Royce, AWE, TWI, Morgan Materials. So it's about bringing that expertise to bear to encourage young people to think about reading engineering at large and materials science in particular. So we fund university places, we fund postgraduate education, we fund vacation studentships. But for us, the icing on the cake always was something we set up 30 years ago. The pinnacle of academic achievement was a medal we established with the Royal Society, which is the Royal Society Armourers and Braziers Medal, which is actually 30 years old, given every 2 years. But what has happened in the years since then, of course, is that materials science and engineering underpins so much of engineering. If you think about my own area, regenerative medicine, new biomaterials, as we heard with Bob Langer, are actually changing and transforming medicine. And at the other end of the spectrum, all as we pull out our iPhones and we touch that screen, all that is happening because of clever, innovative materials. And what was obvious to us as a company is that we needed to actually balance the Royal Society Award with another prestigious award at the top level. And that was where we entered into discussions with the Royal Academy. And I'm delighted, in fact, that we ended up establishing this adjacent medal, equally prestigious, which is to recognize the particular skill of looking at clever material science, but actually translating it into industry to the benefit of industry and to the benefit of engineering. And I'm delighted that process has gone through. And tonight is a very special occasion for us as a company because this is our first winner. And we were completely independent. It went through the awards committee. And I shall now we're inside the 25. I'll give you the pass back and say, we're ready to hear about the winner.
I'm really delighted to announce that our inaugural winner is Judith Driscoll, Professor of Materials Science at the University of Cambridge. Her research has revolutionized the properties of high-temperature superconductors, enabling them to carry much higher currents in a magnetic field. By creating nanostructured superconducting thin films, Professor Driscoll has merged the properties of composite materials and electronic materials, and this has transformed conventional thinking and generated hundreds of millions of dollars worth of investment in research in these new materials. Her methods are becoming widely used in wind turbines, motors, and RMI, as well as in the very high magnetic field magnets for basic science experiments. Judith, will you please join Bill and I to receive the award? Judith, congratulations, and Bill, thank you very much. I now have the honour of introducing our New Year reception speaker, Philippe Mellier, Chief Executive of De Beers Group. Philippe began his career at the Ford Motor Company, where he spent 19 years in various senior management positions. He joined Renault as a senior vice president, and in 2001 moved to Volvo AB to become chairman and chief executive of Renault Trucks and a member of the Volvo Group Executive Committee. Before being named chief executive of De Beers Group in May 2011, he was executive vice president of the Alstom Group. Tonight, Philippe will share the role that innovative engineering plays in the modern diamond industry. Trapped beneath the earth for 1 billion years and treasured across continents and cultures, diamonds have a remarkable story to tell. From large-scale, billion-dollar mining operations to the microscopic precision required to unlock the value in the world's most concentrated form of wealth. Engineering and technology are part of the story of every stone. Tonight, we're going to hear that story, and I'd now like to invite Philippe to give his lecture entitled Engineering Forever.
Thank you. Thank you very much.
Thank you very much.
Our story begins where light began. Light touches everything we do. As we explore, as we discover, as we inspire. Since 1888. A symbol of commitment. As our story ends, theirs begins, and our pursuit of brilliance goes on.
3 billion years ago, as the continents took shape, quite a long time ago, hundreds of kilometers below the Earth's surface at pressures 50,000 times over the normal atmosphere pressure, and at temperatures of up to 1300 degrees, a crystal, very special crystal lattice structure was formed, diamonds. They formed in subcontinental lithosphere 125 kilometers to 200 kilometers down below, and some very rare diamonds may have been originated down to up to 600 kilometers below us. Powerful volcanic eruptions forced magma through the Earth's upper mantle towards the surface at the speed of sound. As the volcanoes eventually cooled, the diamonds remained trapped inside vast cones of hardened magma, or kimberlite, because the first one was found near the town of Kimberlite in South Africa. I'm sorry, I'm just realizing I'm not in front of the geological society tonight, and don't worry, I'm going to talk a little bit about engineering. Thank you, Dame Anne, lords, ladies and gentlemen. Thank you to the Royal Academy of Engineering for inviting me tonight and to share with you my passion, diamonds. And I've been in this business for 5 years, and I'm pretty sure I would like to transmit my passion to all of you. But to start with, I just brought you a small sample of what we mine. Obviously, for those in the front, it's quite easy. For those at the end, it's a little bit more difficult. But this is a 300-carat diamond. This is why we have so much security downstairs. If it's not a very, very good quality diamond, so we won't cut and polish it. But if it was a very nice diamond, white diamond, it will be worth at least $50 million. This is to show you that there is quite a big store of value around here. Diamonds are indeed a treasure of nature and a marvel of geological forces. But the story of diamond is one of seemingly unsurmountable odds and impossible settings, and it has been going on for many centuries. It is a story of scale, of the very big and of beyond what can be seen with the naked eyes. It is a story of multi-billion-dollar capital projects that stretch over kilometers, and of the microscopic precision required. We are working on one of the world's most concentrated store of value. This is the story of problem solving. The story of diamond is truly a story of engineering. 81 billion, this was the size of the global diamond jewelry market in 2014, with the US making approximately 40% of the world market, followed by China, India, and Japan. Broadly speaking, consumer demand for diamond is rising across the world, and we expect it to continue to do so. At the same time, available production from diamond mining is expected to plateau in 2 to 3 years from now over the coming years. Growing consumer demand will outpace production at that point in time. And we all have to understand that we are a mining company, but before that, we are a luxury consumer-orientated mining company. And the only source of value for De Beers, for the diamond industry, is the desire for diamond jewelry. Everything starts with the consumer. And that leaves us with a big challenge. We are, after all, the world-leading diamond company. We have by value 35% market share. We are not the biggest miner in terms of carat. The Russians are mining more diamond than us, but by value, our diamonds are better than the diamond mine in Russia, so therefore we are the #1. Diamonds today are both rare and finite. We know that more every day. In fact, if you had every diamond cut and polished throughout history, since the history of diamond began, they wouldn't quite fill up one London double-decker bus, and we will still actually have some room for the driver. So when you have this one, and you look at this one in the street tomorrow, They said that all the diamonds been cut and polished since the beginning of the story of diamond could fit in one of these. So a lot of value in a very small space. So that requires De Beers as a company to focus on three things: maximizing the life of our current production, finding out and investing in new supply, and enhancing the value of our supply right up to the moment it is placed on a woman's finger, the final destination. There are undoubtedly people in this room, I hope, right now that are wearing diamonds. I think I saw one or two examples. And as I speak, somewhere in London, I'm pretty sure of that, there is a man down on one knee presenting a diamond to a woman he loves. The diamond he is giving to her and the diamond you have either given or received yourself represent an epic journey. And this is what I'm going to talk about. For your reference, 87 of the couples being engaged in the US are exchanging a diamond ring today as we speak, 87%. So let's take a step back. If there is one thing I have learned since becoming CEO of De Beers around 5 years ago, it is that it is an industry of very big numbers and even bigger odds. 6,800, this number is very important for us. 6,800 subterranean kimberlite pipes, these famous extinct volcanoes, have been sampled mostly by De Beers across the world to determine whether there warrant development of a new mine. Of those sampled, only 1,000 kimberlites contains diamonds. And of those, only 60 deposits around the world are considered to be economic to be mined. De Beers is interested in developing and mining only what we call tier 1 assets, the big mines, meaning that they have the cost profile, diamond value, and mine longevity that we are looking for. Of those 60 deposits considered to be economic, only 7 were developed into tier 1 mines. Just imagine the work to discover 6,800 volcanoes and develop 7 mines, 1 out of 1,000 during the last 130 years. Nevertheless, finding new diamond sources is essential to the future of our business because, as I said, it's going to plateau in 2019. This requires to narrow these odds. Our exploration team searches for diamonds in places like Botswana, South Africa, and Canada. The terrain is diverse, difficult, and there is a lot of it. Often the areas we want to search are remote and difficult to access, and I will give you a few examples of that in a moment. Carrying out magnetic surveys from the air to identify the telltale signatures of ancient and eroded kimberlite pipes is common exploration practice within the industry and has been responsible for many new finds in the last decades. The problem is that these surveys are not effective in certain locations, particularly magnetically busy areas because of the presence of banded ironstones or dike swamps. De Beers has pioneered a new airborne technology, an industry first, which works in places where traditional systems struggle to operate. A 10-year joint development project between IPHT, Institute of Photonic Technology in Germany, Spectrum Air, Anglo-American, and De Beers created an airborne system using superconducting quantum interface device technology, or SQUID for short, as we call it. Originally engineered in the 60s for primarily medical application, it has since been adapted to create a system that measures and records how components of the Earth's magnetic field change in different directions. It can do this from a height of around 25 meters above ground while attached to a high-speed moving helicopter. And we have a picture of this one just in front of us. This one was taken in South Africa. The sensitive magnetometers can detect changes in magnetic field that are 100 billion times weaker than a typical fridge magnet. At the heart of a squid is a device called a Josephson junction, two superconductors made of niobium separated by a thin insulator through which electron can pass. An electric current is applied to squid, and minor variation in magnetic field can be detected as changes to the system's electrical resistance. As niobium only acts as a superconductor temperatures close to minus 273 degrees centigrade, it is necessary to cool the squid by housing it in a cryostat, a container that uses a refrigerant such as liquid helium to maintain it at an ultra-low temperature for supraconductivity. The system that we have developed internally in the beers is a complex piece of apparatus made of up to 6 squids, 4 magnetometers, an altimeter, and GPS equipment, plus a wireless network system to transmit the data live back to the helicopter. And all of this is contained to this thing which is looking like a small fish here. Crucially, the new technology means that we will be able to search quickly and effectively in unexplored areas. For example, during the first test survey in the Northern Cape, South Africa, where this picture was taken, squid highlighted a previously undetected anomaly in the land below, while drilling later confirmed to be a kimberlite. This is an exciting innovation for us, and we estimate that it will make our surveys between 33 and 50% more productive in the search for diamonds, giving us a significant advantage over other competitors. Once the diamond deposit is found, it needs to be developed. Minus 40 degrees, that's probably not far from the temperature as I speak at our newest diamond mine, not far from the Arctic Circle in Canada's Northwest Territories. Despite freezing conditions and no road access for most of them, the Gachokwe mine, the name of the new mine, is moving swiftly toward production later this year. This is a picture of the mine. Gachokwe is the largest new diamond mine under development globally. Exploration work started about 20 years ago in the Kennedy-like area when pipe 5034 was discovered by Mountain Province Diamond, an exploration company. In 1997, Mountain Province Diamond and De Beers formed a joint venture. The project was given the name Gachokwe, which means in the local language of the Indians there, a place where there are big rabbits. I have never seen one, but it seems that they had one in the past. Construction began in December 2013, and the mine is expected to begin operation toward the end of this year, in line with budget. I'm saying that to the chairman of Anglo-American, in line with budget, no problem. Sir John, located about 280 kilometers northeast of the Northwest Territories capital, Yellowknife. Today in Yellowknife we had minus 32 degrees. It was a warm day. The mine has 4 identified kimberlites, 3 of which are economic to mine. The pipes are in the southern part of the Kennedy-like district, and because of their shape and size, open pit mining is the best method to access the kimberlite, this famous lava. To mine the deposit, the water level in Kennedy Lake will be lowered by dewatering pumps, and we have been dewatering for the last year and a half. The water on site is controlled by building a series of dikes, ditches, burns, and ponds. Clean water is then pumped to the watershed north of the lake and return to the natural outflow later. We expect to move more than 350 million tons of material during the mine's life, and it's expected to trade around 35 million tons of ore, yielding 54 million carats. We expect to mine some 4.5 million carats each year for about 13 years. Before work began, we oversaw several years of environmental studies and community engagement project to minimize the impact of the mine. If you look at the mine is right at the top where you have the building behind the tanks. Top left you have the runway, and here you have all the truckloads which came through the winter road. The winter road is something very special. As well as the ordinary challenge of a large-scale project like this, which is a billion-dollar project, the difficult terrain and its isolated location threw up obstacles. We only have ice road access for 2 months of the year to resupply the site. The De Beers spur of the ice road stretches some 120 kilometers, 112 kilometers of which travels over bodies of water. It takes more than a month to build the ice road, and we are starting the 2016 ice road right now, pumping up water from beneath so the ice becomes thicker and thicker, up to 1 meter thick. About 2,200 loads of fuel, construction supply, mining equipment and other materials were delivered along the road in 2015. The trucks must meet rigorous safety standards, carry extra fuel, emergency supply and survival gear, and they always travel in convoys. But finding new diamond deposit is incredibly rare, and most of our energy, resources and capital are focused today on expanding our current mines. Half a world away and about 80 degrees Celsius warmer, 500 million tons of waste rock encapsulate diamond-bearing ore at our Jwaneng mine in Botswana. Jwaneng is already the world's richest diamond mine, and this is now the site of one of our largest ever mine expansion program. The scale of the excavation is huge, taking the 2.5 kilometer by 1.5 kilometer mine from a depth of 400 meters to a depth of 650 meters, which is going to make this diamond mine one of the biggest man-made holes in the world. Just brought you a small film to show you how we are blasting in Jwaneng. Looks small on the picture, but we just blew like 3 or 4 million tons. The scale is quite gigantic there. It is an engineering feat that includes many people, including approximately 2,200 employees and 3,000 contractors. Every day, they are removing 24 hours a day, 340,000 tons of waste rock and 23,000 tons of ore from the open pit. This project will extend the life of Jwaneng mine at least until 2033, providing access to 91 million tons of ore containing an estimated 110 million carats of mainly high-quality diamonds. This project is critical not just for De Beers, but for Botswana. Our partnership with Botswana, the government of the Republic of Botswana, which is also a shareholder of De Beers, is really to mine and sell the diamonds from the country, and we generate together $4 billion for the Botswanan economy in 2014. These $4 billion of wealth represent about 25% of the country GDP, and it is double the contribution of the whole wholesale and retail industry in Botswana. 25 years ago, Botswana was the poorest country in the world. Thanks to diamond, today, Botswana is a middle-income country and one of the richest per head in Africa. Just south of Botswana, at the border with South Africa, 2 vertical shafts reaching depth of 1,080 meters, more than a kilometer, are built at our Venetia open pit mine to transform it to an underground mine by 2021. It's a $2 billion project. It's going to enable us to extend the life of the mine till 2043, and the project is expecting to treat approximately 133 million tons of ore containing an estimated 94 million carats of diamond. Everything on this scale, and it's such tight spaces. The two shafts, you have the picture here of a shaft being built just from the bottom of it. We are just at the beginning of it now. Two shafts are each just 7 meters wide. They require very special technical skills and single-minded focus on safety. We had no fatality in De Beers for the last 2 years, and we employ more than 30,000 people. And it is the safety of our people that we continue to invest in by funding innovative ways to operate. In everything we do, safety is coming first. One example is in the studies that we are carrying out to test the feasibility of automatizing potentially hazardous part of the mine. Potentially, this new mine underground will be fully automated by 2021. However, the only thing any diamond miner will tell you is if you are going to go to where the diamonds are, wherever that may be. You may be surprised to learn that De Beers is the world's largest marine diamond miner. We mine diamonds from the seabed at depth from 90 to 140 meters in the Atlantic Ocean off the coast of Namibia. The Orange River that carried diamonds from the center of South Africa, near Kimberley, millions of years ago, also deposited its precious cargo across the ocean floor and did a lot of sorting for us through the millions of years. Our fleet of 5 mining vessels screen material recovered from the ocean floor. These deposits are then lifted by helicopter for further processing on shore in Namibia. We use 2 methods for our marine operation: horizontal marine mining and vertical marine mining. This is a ship, this vessel is with a derrick for vertical marine mining. I'm going to show you a very short film of what we do from a horizontal marine mining perspective. It's a very short film. I just wanted to describe it before we see it. We have a huge piece of equipment which is weighing 170 tons on the seabed floor, around 100 meters deep. And it's being tied up to the vessel by a huge hose of 70 centimeters. And we are vacuum cleaning the bottom end of the sea. We are bringing all the gravel back, and it is treated there. I'm going to show you a small film where you see the vacuum cleaner being operating down there and how the vessel is being positioned. And you are going to see also the piece of equipment being brought on the vessel. So this is the piece of equipment. This is the biggest vacuum cleaner on Earth. And you're going to see it working. It's very efficient. This is the positioning of the vessel by pulling on the anchors. We can mine up to sea, up to 9 meters high. And this is the piece of equipment. It's unique. It's designed by us, it has been developed by us, and it is proprietary technology. This piece of equipment is mining 600,000 carats per year, and these diamonds are the very best in the world because they have been sorted by nature. Looking across our production footprint, last year De Beers mined more than 28 million carats from open pit, underground pit, alluvial and marine operations across 4 countries in 2 continents. So this leads to an obvious question: what do we do with all these diamonds? And this is a question I would like to answer right now. 12,000, that's a magic number for us. This is the number of price points we divide our diamond assortments into for sale. Every diamond is unique. Determining its shape or model is a key part of the sorting process when we worked out of the mine with what we call the run-of-mine diamonds. That's where we often determine the final size and shape of the polished jewel. Sorted diamonds are scrutinized by clients who are supplied with a rough diamond they need for their diamond cutting and jewelry making requirements. But with so many categories, it takes more than a trained eye and years of experience to get our distribution right. It takes cutting-edge sorting technology. The De Beers Technologies team have developed differentiated technology for us to sort diamonds based on their color, clarity, and carat size. Enables us to provide our customers, our clients, with consistent and reliable assortment. When you look at an assortment from De Beers for special type of crystal, it looks like they have been done by a machine, but they are all natural, they are all different, but they have been sorted and put together coming from all the mines around the world. Our fastest sorting machine can sort diamonds at 15 stones per second. But as I said, every diamond is unique. So our team has had to work to figure out how to keep a constant feed of irregular, often friable, and always valuable rough diamond at such high speed. Our sorting machines are camera-based. They pick up stones and place them on a measurement cell where the key value determining information is extracted from the image in less than 100 milliseconds per stone. Just imagine we throw through a circle where you have 10 extremely high resolution cameras. You throw 15 stones per second through a hole. Each time the stone goes through the hole, the picture is taken, and in 100 milliseconds, you can get the color, the weight, and the size of the stone, just by looking at it, photographing it, treating the image, and after that you can sort it. And this is all proprietary technology. Obviously, we don't share it, and has been developed for many years. 30 years ago, we had in London more than 1,000 people sorting diamonds. I think today we have 50. And the sorting is much more accurate. Diamonds have a unique physical property which makes them useful in a number of areas you are probably not aware of. Element 6, and you have seen a small display downstairs if you stop just at the right at the entrance, is part of the De Beers Group, and it's a world leader in the production of synthetic diamond material for industrial and technological applications. Element 6 Global Innovation Center in Oxfordshire is the world leading research facility for synthetic diamonds. It has more than 140 scientists, engineers, and technologists. And I think we have 59 PhDs there, dedicated to product development for diverse industries, including oil and gas, where we should be today the biggest supplier of drill bits for oil and gas industry, precision machining, healthcare, water sanitation, electronics, and many other applications. The last application was, if you follow the car industry, the latest diamond tweeter in the latest BMW 7 Series are made of a dome of diamond, and we are the supplier of the diamond dome for the tweeters for BMW. One recent example of groundbreaking innovation is Element 6 Atlas Press. This is the press, and we have some parts of it we don't want to show too much, so we have erased a few details. It was installed in our Global Innovation Center last year, and it is the only one of its kind in the world. The result of the multi-year innovation project for De Beers and Element 6, the Atlas Press represents the very latest in high-pressure, high-temperature diamond synthesis technology. Usually, you were having belt presses. We could generate 6 to 7 gigapascal. This one will go well over 10 gigapascal, so we will expand the world of synthetic diamonds, and we hope produce diamonds which are going to be stronger and more durable than the natural diamond. Turning back to natural diamonds that end up in jewelry, we are looking at the extreme challenges presented by exploration, extraction, and sorting, but some of our biggest challenges are not about volume efficiency, but rather about confidence and integrity. Here too, the application of innovative engineering and technology-based solution has led us to industry first. And ultimately, a diamond is an emotional purchase. We all know that. Whether you are buying yourself or someone else, you are usually making a statement of commitment, love, celebration, or pride. So when people buy diamond, they deserve to have full confidence that they are getting the real thing. For decades, De Beers has been focused on protecting a consumer's confidence in diamond. And we have developed screening technology that can detect all undisclosed synthetic diamonds. With more companies producing synthetic diamonds today, we have proven our ability to stay several steps ahead and detect new efforts to pass off synthetics as natural diamonds. We push element 6 to try to develop synthetic gems that we will beat with our machine. So it's a race between element 6, trying to push the envelope to have nicer and nicer synthetic diamonds for industry, but could be used for gems application. And after that, we try to detect them. So far, none of them went through without being detected by the machine. This is the latest machine we have developed. We have a collection of machines called Diamond Sure, Diamond View, Diamond Plus. The new machine is the automatic Mellier screening machine, which allows to screen automatically very small diamonds at very high speed. I'm just going to give you an example of what we can do with this. Obviously, it's a little bit of a closed box, but inside there you have state-of-the-art optical engineering to detect through some very special lights if a diamond is not a natural diamond. 1/20th of a micron. Forever Mark, the diamond brand from the De Beers group of companies, which has a strong presence in the US, China, India, and Japan. We have just launched Forever Mark in the UK 6 months ago. Carries an inscription on the table facet of the diamond, which is 1/20th of a micron deep. This is an example of what we can do with this. You can see the inscription there on the table of the diamond with a proprietary, obviously, technology. We inscribe the logo of the brand, the Forever Mark logo, and the number. We sell the diamond with a card, a chip, on which you have the number, and we can trace the number. Even if the diamond was stolen, by reading it, we could find it and send it back to its owner. So diamonds are making a very remarkable journey from mine to finger. But in the end, there is only one thing that is beyond the scope of engineering. I'm saying that in front of this distinguished audience. And only one number that really matters. The one love that your diamond represents. And this part is for all of us.
Billions of years lying in the dark, waiting for this moment. Time has forged my character to be strong and pure. While I waited to be discovered and selected amongst hundreds, me and me alone. Finally, my true beauty has been brought to light. And after a long journey, I am here to light up her smile forever. Forever Mark. A diamond is forever.
This is the advertising campaign we had on TV in the US and in digital media during the selling season, where around $10 billion of diamond were sold in 3 weeks. We are the leader. We have created the market 130 years ago. We are still the leader. You don't have too many companies 130 years old creating an industry and still being the leader. And I hope I pass the message that yes, we have a lot of engineering and technology, and we are at the really top end of our technology, from mining, exploration, to detection and selling diamonds. But first of all, we are a marketing company, because the only source of value is in the desire for diamond jewelry. And if we all understand that, we understand what De Beers is all about. Thank you very much.
answer some questions from
Yes,
you?
I'm sure. Yeah.
The plan is we just sit down over here and wait for the microphone before you speak. So, do we have questions, please?
Yes, thank you very much for a very interesting talk. My name is Simon Watts. You're processing thousands of tons of kimberlite a day in a mine. What percentage? How do you actually extract the diamonds from the kimberlite, and what percentage of those diamonds are gem quality as opposed to machine quality or whatever?
The average grade is 1 carat per ton of ore. A carat is 0.2 gram. So in the richest mine in the world, I was talking about Zhuaneng, we mine 12 tons of waste for 1 ton of ore. So for each carat of diamond, 0.2 gram, we mine 13 tons. So now you understand the diamond is rare. And it's also quite expensive to mine. It's pretty simple. We don't mine by hand. We are not in platinum or gold mines. We are, as you have seen, in huge mines, and we have huge fleet of 300-tonners trucks. So we have we drill and blast. After that, we have huge shovels, and we load the trucks. This is why we can, in one mine, extract 350 or close to 400,000 tons per day. After that, we crush down the ore down to around an inch. So it goes in different stages. At each stage, through X-rays and laser, we can detect diamond in the ore. And we have an automatic system. Obviously, all of this is proprietary to guide the right ore potentially containing diamond into the next cycle, so it's recrushed, and the rest is being dumped at the different stages of the plant. So we don't crush everything. We have the primary crusher crushing everything, and after that we go down in the size only if there is a probability to contain diamond. We have a high percentage of diamond quality. Let's say 60 to 70% of what we mine is gem quality. Gem quality doesn't mean automatically DEF colors, the whitest diamond. You can have a brownish, yellowish diamond, which is not the top quality, but it's still gem quality, especially, for example, for the Indian market. I was talking about the Namibian diamonds. Nature has sorted the diamonds, and the weakest one broke. And the one which were left, like this one, this is a perfect crystal. It's like two pyramids stick together. In Namibia, we mine quite a few of those, not the same size, but this type of crystal, which are very, very nice. And more than 90% of what we mine in Namibia are of gem quality. This type of crystal, you cut it in half, and you make it round, and you have 2 round diamonds. It's pretty easy to manufacture, and the yield is very good. So if we go from rough to polished, the average yield, I would say today, will be around 30 to 40%. So if you mine 1 carat of rough diamond, as an average, you will get 0.3, 0.4 polished diamond to be set in jewelry. This is the ratio. So in Zhuaneng, for example, 13 tons will lead maybe to, 0.3 carat. So it's really very small.
Thank you. Do we have another question? Rick?
Rick Parker, Rolls-Royce. Do you you showed us an interesting example of subsea mining and hoovering up all this stuff off the seabed. Is that a promising area for the future? Is De Beers investing more in that going forward?
Yeah, we have been approached by other type of miners, and we are researching for the time being what we could mine. And off the coast of Namibia, we are mining gold and platinum. But for the time being, we are rejecting gold and platinum because we don't know what to do with it. I shouldn't say that. But we have now a micro plant in our biggest vessel to understand how we can maximize the recovery, because what we get today is by accident, and to try to see what we could do to recover.
Yes, we are potentially looking at it because we have a technology which is pretty unique and could be used for other things, but it's too early to tell today, unfortunately.
Okay. Question there?
Thank you. Roger Venables, civil engineer. One of our major gravel extractors some years ago described that its business as creating nature reserves with a gravel byproduct. In other words, they had a plan as to what to do with a gravel extraction site after the gravel had been exhausted. Mm-hmm. I'm just wondering what your long-term business plan is when they run out of when you run out of diamonds.
We are provisioning from day one the rehabilitation costs. And we have closed already, it was before my time, we have sold or closed the first mines in Kimberley. Apart from the big hole, which is a huge hole we kept, or the South Africa kept for souvenirs as an history, all the other mines have been filled again. So we are provisioning all the time the money, which can be pretty expensive to fill the hole back. So in Juaning, which is a huge, huge hole, maybe in 60, 70, or 80 years from now, because we have a huge development potential, we will have to refill the hole. And we are provisioning the money for that. In Canada, we have just closed one sub-economical mine underground, and we will just fill it with water. It's just because it's full of water, so we just stop pumping and it will be filled with water. But every country has its own environmental requirements. Usually it's to bring the terrain back as it was at the beginning. And we know that.
Thank you. Further question? Yes.
From the professor. Oof.
Yeah.
Professor Judith Driscoll, just want to say we have sent some students to Element 6. So, yeah, that's good. So, artificial diamonds, obviously people are interested in those. And you kind of gave the suggestion that they'll never really be as good as natural diamonds. Mm-hmm. Is that really true? Or why do you say that?
No, but artificial diamonds are diamonds, but they are not natural diamonds. They are being made artificially. And there is always a very big debate about that. And as we are the leader on both sides, it's very difficult. But and this is about marketing. It's about the desire for diamond jewelry. The real thing is natural diamond because it is extremely old, it's extremely rare, and it has all sorts of emotional values linked to it. And this is clearly something you cannot link with synthetic diamonds. By law, synthetic diamonds or man-made diamonds has to be disclosed by law. So there is a market for man-made diamonds or synthetic diamonds. There is a small market in the US, tiny market, and it's not picking up because the true desire for jewelry, diamond jewelry, is for the natural diamond. And I know that from an engineering point of view, from a physical point of view, it could be the same. But one is man-made, the other one is out of the ground. And this is what is making the whole difference. So it is not very engineering, but it is a lot about emotion.
But part of that question is, do you anticipate a stage where they are absolutely indistinguishable, and it's only by having that marking that you're putting on that you will be able to tell the...
Thanks to the students we have, the PhDs we have, we are always...
One step ahead.
Yeah. You have two ways of making synthetic diamonds or man-made diamonds, high pressure, high temperature, and carbon vapor deposition. The first technology was high pressure, high temperature. CVD is newer. CVD can really produce very nice diamond, but they are too perfect. So the guys who would like to smuggle man-made diamonds into the normal pipeline are treating them after that so that they don't look perfect, so that they look like coming from nature. Right. But we can also detect that. CVD are grown on substrate, and you grow layers of carbon layers like this. But you can always detect the substrate or what remains of it. The latest one is to use a very thin slice of natural diamond and grow synthetic diamond on top of it, so that you can't really find something not natural as the base, but we can still detect that. So we go down to the atom level to detect if it's really natural or synthetic, because we know all the technologies to manufacture synthetic diamonds.
Thank you. Further questions? Philip?
Philip Greenish from the Academy. You didn't talk much about industrial use of diamonds. I get the impression that non-gem quality diamonds that come out of the mines are almost waste products,
yes.
Especially if synthetic diamonds are presumably used mostly for industrial use. Is that the case?
That's the case. We, let's say 20-30% of the diamond we mine are industrial quality. We sell them, but we sell them for 2 or 3 cents per carat. It's nothing. And usually these diamonds are crushed. They don't have any life in them. They are all dark and black, and they are crushed, and they are used on diamond wheels to cut and polish diamonds after that. We produce, let's say, 30 million carat per year. We are going to produce maybe 5-6 million carat of natural industrial diamonds. And we are one of the biggest producers. The world production of man-made diamond for industry is 3 billion carats. So it's a very, very small proportion. Very, very small proportion. But we still sell them, but it's not making our living. A carat can be 5 cents or can be $50,000 if it's a white diamond. And if it was a yellow or pink diamond, can go to $1.5 million. The same carat, the same weight, can be 20 cents or $1.5 to $2 million. So this is why not 2 diamonds are the same. And this is what is extremely interesting in this business, because we know the grade, we know it's 1 carat per ton of ore, but we don't know which carat. And the other day, we mined close to a 400 carat diamond, and it makes your day. Clearly, even if it's in a big mine, you can clearly enjoy it. But some other part of the mine, you have low quality. You have to mine through that to go to the next stage, and you know that the average price will be lower. This is what is making this business extremely exciting. It's not like mining coal. You know what to expect. We know the grade. We don't know what to expect.
Oh, yes, go ahead.
My name is Basil Butler. As my name is Basil, you will realize I have a considerable interest in the security of diamond jewelry in London. But can you tell me what is is it a serious problem looking after the security of the product in the field end?
Yes, it's a serious problem, but I would say we are used to it. And if you are on a mine or in our offices, you will see that we have a lot of security. You don't always see it, but to start with, at the mines are always surrounded by a perimeter of security. And in Botswana and South Africa, these are very big holes. We have very big security perimeter, which usually are used as game reserve. So they are so big that we can use them as game reserve. In fact, we have reintroduced rhinoceros in Botswana in our game reserve around Orapa, which is our second biggest mine in Botswana, because it is very safe. The army is there, and no poacher will dare to go there. And so it's very difficult to access. In the mine, we have very, very tough security measures. When you enter the mine, when you exit the mine, you have cameras absolutely everywhere. And it's extremely difficult to take a diamond. It's forbidden to touch the kimberlite. It's forbidden to be in touch with the final product, except if you are right at the end, because everything is automated. You can be in touch with the product when, at the last stage, of discovery, the diamonds are falling in a small tin. You say, poop, poop, you hear the noise, the diamonds are falling. This is where you are in contact with the product. Before that stage, you don't have to be. I can share with you an anecdote because I'm French, as you can hear, and I am not very, I am always out of control. And I was at the bottom of the pit in Joineng, the biggest, the richest one. And the central pipe, the center pipe is one of the richest in the world. The grade can go up to 5 carat per ton, which is huge, 5 times the average. And I was talking with the guys, and they said, I've been working here 30 years. I have never seen a diamond. And that's true. 30 years in the richest mine, he has never seen a diamond. And, being French, out of control, I did what I shouldn't do, but they know me. So I took a piece of kimberlite, which was just on my feet there. Kimberlite is lava, which is it's a greenish type of lava, very strange type of lava. And there was nothing there. I turned it, and we had 2 diamonds. and the guys were absolutely astonished. They were shocked. And you could see the 2 heads of the diamonds there. And obviously, everybody looking at me, I put it down. And because I'm out of control, I took another one, and there was another diamond there. So in let's say, 30 seconds, I found 3 diamonds, when guys being there 30 years didn't see one. So it was quite interesting. But it was pure luck. I should have played with the lottery on that day.
Well, Philippe, thank you very much. You've given us a really fascinating lecture, a glimpse of what goes on behind the diamonds that, speaking as a woman, are very much appreciated when they arrive in our hands. But a really interesting lecture. Thank you so much. And I'd like to thank everyone for coming to this New Year. A little bit late to be calling it a New Year, but this New Year event. And I hope you'll join us now downstairs for the buffet supper. Thank you very much.
Thank you.